let me start this. This work was based on recent work with Minxin Huang of China and Xin Wang of Kias, and also my previous work with Jin Chen, Babak, and Hichel, Marcos, Xin Wang. So this, let me talk about Wilson loops in 5D and 6D. Wilson loop was introduced in 70s as a tool to explore strongly interacting gauge theories. So Wilson loop represent physics of infinitely massive quarks in given representation with world line C. So one can use, for example, in Euclidean time, this square box. So Wilson loop expectation value, which one can obtain by path integral, tells us whether theory is in confining phase or Coulomb phase, depending on how expectation value decreases the size of the Wilson loops. For example, in confining phase, Wilson loop will decrease with area loss, and Coulomb phase it decreases perimeter loss. In the last 20 years, in various supersymmetric field theories, Wilson loop has been explored to reveal the various secrets. More recently, for example, space-like Wilson loop operators can be regarded as a charge-carrying operator under one-form symmetries. This is quite interesting, but I don't have time to talk about this in this meeting. So outline of my talk is given in here. So first, let me introduce 5D and 6D superconformal field theories. And then I'll talk about 5D Wilson loops and the 6D Wilson loops or Wilson surface. And I will conclude with some remarks. So 5D and 6D quantum field theory is, they are usually non-renormalizable and infrared free. So they seem to be uninteresting. However, for last 20 years, there have been found, this theory has been found to have a UV convolution. And at UV, they carry supersymmetric conformal field theories, superconformal symmetries. And there has been a complete classification of 60 superconformal field theories. And also there have been many good attempts for classification of the 5D superconformal field theories. One can learn many non-trivial things about these theories by studying the partition function on R4 cross S1 or R4 cross T2 with omega deformations. Now, exploring these theories, some external probes like PPS surface operators and Wilson loop operators have been quite profitable. In this talk, I'll focus on physics of these theories with Wilson loop probe or codimension 4 defect. And they generate a new kind of Kopakuma buffer invariant and also give a light on the quantization of Seiberg-Witten curve in NS limit. Now, partition function on R4 cross S1 or 5D theories can be studied by considering the theory in Coulomb phase of 5D theory, for example, which has SU2 R symmetries. Now, given supercharges, we look at the Witten index. And let me move this. Witten index, and here we introduce various chemical potential for charges which commute with these supersymmetric operators. So J1 plus JR, J2 plus JR has a chemical potential epsilon 1 and epsilon 2. Basically, this epsilon 1 and epsilon 2 characterize the omega deformation. And then for flavor charges, one can introduce flavor mass, and for gauge charges, one can introduce Coulomb parameters. And this necklace of partition function can be calculated in various ways. And especially theory with non-abelian gauge description in IR, one can do instanton expansions with instanton mass parameter expansions. And this partition function is made of the Potovich part and instanton part. And basically, this partition function measures the massive charged part object, which is made of flavors, W bosons, and instantons. And the perturbative part methods basically quantization, one loop corrections. And instanton correction can be written in some of the contribution from K instantons. Let's see this. And for a 60 series, we have to calculate the instant partition function of alpha cross T2, and all the 60 superconfirmed fit series tensor branches, and you could have vector multiplet and hypermultiplets. And similar necklace of partition function is defined on alpha background with the charge and the various other chemical potentials. Especially in 60 theory, one can introduce chemical potential for KK momentum along the circles. Now, this partition function can be again can be calculated in various manners. Especially, one can written in terms of stringy contribution expansions. So one can have a perturbative contribution, which is Mercedes particle in 60 moving with speed of light along the circle contribution, plus string for there's strings for each tensor multiplets, and then for given string contributions, one can have a partition function. This string contribution can be obtained as an elliptic genus on two-dimensional physics on n strings.
Can I ask a question?
Yeah.
Yeah. How much supersymmetry do you need for this?
Also, in this case, either you can have 8 supersymmetry or 16 supersymmetries.
So like n equals 0,2, 0,1?
1,0 or 2,0, both cases one can calculate this partition function.
I see. Okay, thank you.
Now, interestingly, this 5D or 60 partition function can be written in very interesting form. As I said, this partition function is counting the composite object of W bosons, instantons, and also flavor symmetries and KK momentums and so on. And so this counts the degrees of freedom of a BPS object. But this partition function, as it is, even though it captures the index, it doesn't count the degeneracy of individual particle. We have to put this partition function into exponentiate, and so that we get a free energy. Then we have to put it in plastic forms, plastic exponential forms, and then we get this free energy, which we call Kupakuma Buffer free energies. And this Kupakuma Buffer free energy is extremely simple form, really beautiful form, and it's some of the charges. So Q beta is the basically chemical potential for momentums, electric charge, and flavor charges, and so on. And so it's power of the various quantities, and the beta captures the charge of the single object. What it means is that single object which carries the various angular momentum, J left and J right, of the SU2 cross SU2, which is rotational symmetry of SO4 over R4. And this factor, free factor, is made of the 3 bits. So J left and J right is the character for SU2 angular momentum J left and SU2 angular momentum for J right. Now, this pole term is really interesting. This pole term is the basically one, because in R4, we cannot localize the origin unless we turn on the omega deformation. And this pole term is basically which gives orbital angular momentum of the whole object and localized at the origin. So having a single pole means it's made of the single object. If it has a double pole, then it will made of the 2 objects. Both of them are localized at the origin. So this simple pole appears only for when we put it in plastic form. And if we expand the whole object in exponential and then expand it further, then this expansion will have various multiple pole structures. Now, -1 to this quantity captures the spin structures. And then this integer n is non-negative integer, and that tells us that degeneracy of the object. So for given charge beta and the given angular momentum J and JR, how many objects are there? For example, sometimes it can be 1, 2, 0, and so on. Especially SU2, this when J left and JR is equal to 0 is counts the massive hypermultiplet, and J0 1/2 is the massive vector multiplet. For example, 5D SU2 discrete tensor level zero theory without flavor, one can have 2 massive vector bosons. So this will be 2. For given angular momentum, there are 2 objects. There's one coming from W boson and another one coming from instantons. So let's look at the partition function. It's 5D Wilson loops. Now we are interested in PPS Wilson loops. So instead of just introducing line integration of the gauge field, we do integration with combination of the scalar field. So you can see right away supersymmetric variation of A0 and phi can be canceled each other with and this Wilson loop breaks the supersymmetry by half. So introducing this Wilson loop is basically introducing infinitely massive point particle of zero spin at origin. Now this introduction modifies Hilbert space because W bosons and instantons interact with these Wilson loops. So partition function will be some of this modified Wilson Hilbert space with this previous similar indices and similar chemical potential turned on. Now expectation value of Wilson loop is a ratio between Wilson loop partition function and the partition function without Wilson loops. And again, this can be expanded in this nice form where now because we have Wilson loop, then it's interacting with W bosons and instantons. And so they can carry non-trivial angular momentum, which is J left and J right. And they can carry non-trivial charges, number of instanton numbers and the number of W bosons and so on. So D captures the charges and this captures the spins. And turns out there are more structures in there. Turns out that this, when we expand it carefully, this expansion turns out to have not only degeneracy and spins, and also turns out to have zero structures with a charge. So when we do the Kopakuma-Baffa invariant for single particles, we had 4 structures. So this inverse of pole, which is H, and there's non-trivial powers of that, and this is the number of zeros. So S equals to 0 will be 0. There's no zeros, and the S S can have some integer powers to some maximum value, and this maximum value will depend on the representation of the Wilson loops. And so this quantity can be regarded as a generalized Kopakuma-Baffa invariance. And there are many methods to calculate this Wilson loop expectation value. And for example, by looking at the gauge sigma model on instanton dynamics at the presence of Wilson loop has been explored. And also recently, Blow formula has been explored to calculate this expectation value. And here we use also topological vertex method and holographic anomaly equations.
So what's the meaning of this extra structure? Does it represent a bound state or something?
Right, exactly. So this tells us the pole structure, bound state of the Wilson loop to W bosons and instantons. So when we have a Wilson loop of higher representation, so some of Wilson loop will be bounded with instantons and W bosons, but they will be they could have multiple bound states or many different states. So the detailed structure is captured by zeros of these contributions.
Mm-hmm. Thank you.
So GLSM has been explored in many directions, but one of interesting work was done some time ago at KIAS by Scarapa. And here is the PQ5 brain web for SU2 Chang-Simon level 0. discrete Chern-Simon level 0, not theta 0. And the way introduce Wilson loop is introduce T3 brane, which is basically positioned orthogonal to T5 brane, NS5 branes. Here's the direction of the T5 and NS5 brane, and remaining 3 directions, 7, 8, 9 direction, T3 brane is there. And then fundamental string connecting T5 to T3 or T3 to NS5 T1 string will be play a role of the Wilson loops. Basically, to be consistent with omega deformation, T3 brane has to be at the origin of the R4, and then the string will be fixed at the R4, and there's no room for string to move along the R4 because it's fixed at the origin of the 3 directions and origin of R4s. Now we can pull out the T3 brane outside. If we pull up, then this fundamental string. If we pull to the right, it's T1 string. And because of this codimensional nature of the this four direction is these 3 directions, fundamental string connecting this brane with T5 brane is fermionic. So they will play like a hypermultiplet connecting the these T5 branes. Now they have explored the instanton dynamics of the K instantons with additional fermions. So without this, it's a standard ADHM dynamics of instantons. KG group SU2 and there's K instantons, but having a T3 brane generate additional twisted multiplet and fermionic multiplet, and they have calculated expectation value of the Wilson loops. Now, Blow formula has been explored more recently. Basically, Blow formula of the Nakajima-Yoshioka Blow formula, which was discovered about 15 years ago, is basically one different way of calculating instanton partition functions. So if we have R4 or C2, then there's origin, which is, then we can blow up to local P1, and then generally the fixed point of the omega deformation is, which is origin, split into north pole and south pole of this P1 was two spheres. And partition function of this blowed up geometry has a 2 contribution, instant partition function has 2 contribution, one from north pole, one from south pole, and then you make a product of that. But interestingly, when we blow up the point of the 2 sphere, one can turn on the magnetic flux on the 2 spheres, and one has the sum of those magnetic flux, and also one can turn on the various background magnetic flux, like flavor magnetic flux. And then this sum turns out to be proportional to partition function without blow up to some proportionality. And if lambda is 0, then it's called the vanishing blow formula. And if lambda is non-zero, then it's called the unity blow formulas. So given partition functions, instance partition function, one can have various blow formulas. They are all constraining or constant equation for this partition function, which is highly non-trivial. And the one can, interesting thing is that this partition function is not just the partition function we talked about, Kupa-Kuma partition function. One has to have also pre-potential coming from the classical action plus one loop connected cubic pre-potential. And with this partition function, they satisfy these nice relations. Now, Hichal and Minsung and Songsu recently generalized this to the case with Wilson loops. So for example, one can introduce Wilson loop because PPS object has to have certain orientations. And if we regard the W boson, which has a charge 2 as BPS, then Wilson loop has to have charge -1. So one can introduce Wilson loop at the origin, and after blow this fixed point, Wilson loop has to be either attached to north pole and south pole. And then one can build up the similar blow formula for Wilson loop expectation values. And then they have calculated various Wilson loop expectation values and confirmed the previous result and also discovered many new things. But let's look at just this case. And then if we look at the classical plus one loop without instantons, so one can regard this charge minus one loop as the fundamental string following this line of the external legs. And because it has charge minus one with minus charge times chemical potential, it gets a factor e to the phi. Then one can have a single W boson attached to and have a bound state. And naturally, W boson is charge minus charge 2. So this has a factor minus e to the minus exponential e to the minus 2 phi. And product together, one gets very nice finely invariant expression for the partition functions. Now, contribution is instanton, so single instantons. One can have an instanton means Dion string connecting these two D5 branes. And so this result they have obtained. And again, this is a finely invariant form. But because we are expanding in terms of the charges, and you can see only object which carries a charge minus one is the classic Wilson loop, then any correction by W boson has to have increasing charges. So if we expand in e to the minus phi, then this is the contribution, how it looks. And then we can expand this e to the minus 2 phi, and then P1, P2 carries some non-trivial angular momentums and so on. So this will generate integer expressions for like the Kupa-Kuma-Buffer invariance object coming from single instant contribution. Now one can do a similar calculation using refined topological vortex method. There has been many works on this subject previously. Especially, I like the work done by Futoshi Yagi and his collaborators some time ago. So this is the answer they wrote down. Basically, refined topological vortex method is instantons and W bosons. They are represented as a Young diagram. For example, D1 string connect on this NS5 brane. If we have multiple D1 strings and there are multiple instantons and characterized by a Young diagram mu1, and also if I have a D1 string on another NS5 branes, another D5 branes, then that will be characterized by Young diagram mu2. And so total number of instants will be side of the mu1 plus side of mu2. So this is the instanton expansion parameters. And mu1, mu2 basically sums over all the Young diagrams and the characterized. So general Young diagram will be no instantons. And then if you increase one Young diagram, zero Young, one, that will be single instantons and so on. And then this contribution is made of numerators and denominators, and they have complicated expressions depending on Young diagrams and also chemical potentials and so on. And also this P1, P2, which is basically related to omega T formation parameter epsilon1 and epsilon2. Now, so we expanded this quantity linear order in Q1 and Q2. So here we choose Q1 and Q2 to be positive, and as expansion parameters, then we expand in linear order. So there will be a dramatic reduction of these expressions, and we keep the remaining part as a W. So here's a linear part in Q1 and Q2, and then still we have to sum over Young diagrams, so which is the instanton numbers, total instanton numbers, and then we call this is the partition function of the Wilson loop for product of two fundamental representation, because Q1 and Q2 is basically flavor charges, and as far as this SU2 is concerned, they belong to fundamental representations, and this belongs to fundamental representation. So we regarded this as just the insertion of the two flavors of Q1 and Q2, and regarded that as a Wilson loop insertion of Wilson loop operators, which we will justify in a minute. Now, reasonable expectation value will be now division of this quantity by partition function without Reasonabs. And of course, this expression is already we obtained from here expansion, and we look at the no instant contribution, and no instant contribution is exactly made of the contribution made up from double poles. So remember, without instantons, this Q1 and Q2 are independent particles. So each one of them is a simple pole. So it will be product of this pole terms twice. So there will be twice of that. And each carries its minus phi plus its phi, because this can carry interacts with these W bosons and then make a composite, and this can make also composite with W bosons. But this W boson are independent. So this is a classic plus one loop part, which is, and now we are interested in case of where this flavor symmetry becomes infinitely massive, which is say Wilson loop, and we can redefine this chemical potential for flavors by observing these pole terms, and then this contribution is exactly what has been obtained previously.
Okay, so sorry. So does the massive limit mean that you're considering Wilson loops in the pure SU2 Young Mills?
Right.
Okay,
right.
And
So
does pure SU2 Young Mills correspond to an IR description of a super conformal field theory?
Not IR yes, IR description of pure, right. So
Sorry?
some sense, right, go ahead.
So does this correspond to a super conformal theory or?
Yes, it is super conformal theory. Of course, here you can turn on the coupling constant SU2 theory. So you did relevant deformation of the theory, conformal field theory, yes.
Mm-hmm.
Right, so here we redefine the chemical potential to observe the poles, then this double poles disappears and we get a contribution like that. So this is exactly what this contribution, product of this, scale of this. Now, let's look at single instant contributions. And turns out it's made of 2 bits. So single instant contribution can have 1, 0, or 0, 1. And then again, you sum them up, then it's made of 2 bits. I said no zeros and single zeros. So if you look at the single zero terms, 1, 0, which means that then this is the contribution they have. So 1 minus P1, 1 minus P2 times these contributions. Okay. So notice that precisely zero terms, all the other expressions has always expression with P1 times P2, P1 times P2 product or division, but never individual P1 and P2. Now, if you look at the expression is no zeros, then there's -2 times P1, P2, then this is the expression. And this expression is exactly 2 times product of the Wilson loop for fundamental representation without instanton, and this fundamental representation with a single instantons. Okay. And this is exactly consistent with what has been discovered previously. Now, so you wonder what is the difference between this term with 1, 0 and the term with no zeros? If we go back to the Kopakuma alpha invariant, then one can see easily what the difference is. So again, let's start with SU2 is 2 flavors. And then partition function, we can put into plastic forms. And then this is the contribution, single particle free energy. And then which has a simple pores. And then usually the way we choose mass parameters such that flavor mass is smaller than Coulomb parameters. And in this case, one can see very easily that global symmetry is enhanced flavor symmetry SO2 flavor, SO4. Is enhanced to SU3 cross SU2 with instantons and flavors merging together into E3 symmetries. But we are interested in different case after flop transition where flavor mass is bigger than Coulomb mass in both cases. So we are expanding this single particle free energy in terms of the this flavor symmetry Q1 and Q2, and we keep only up to the quadratic order in terms of Q1 and Q2 and also Q1 product of this. And each, notice that each expression is a simple force. Now, partition function without Wilson loop is just the exponential of the f zeros, and then with Wilson loop we just expand in this product, and then for scale of the fundamental representation will be have two contributions. One contribution from the product of this, and another contribution from that. So this one is double pulse, and this one is simple pulse. So Wilson expectation value of the fundamental scale of the fundamental representation is made of two contributions. One which comes from the product of the fundamental representation, which is double pulse, and this is single pulse. So now for single pulse, especially in using this calculation, and if I consider only this quantity or that quantity, then we can calculate the Wilson loop 4, because in this case, we turn up the flavor symmetry here. So they would know the presence of this flavor, and they'll know single flavors. So F1Q1 or F2Q2 generate a Wilson loop expectation for fundamental representation. And as I said before, we observe the pole to flavor symmetry. So this zeroth kills of the pole of the F1. And that is the, we can expand in terms of the one loop, classical plus one loop, which, and then single instanton, two instantons, and so on. And they have no zeros and no poles, because we observe that this made of single object, and we observe that pole into chemical potentials. Now, this product of two Wilson loops made of the no zero terms, which is product of these contributions. And now F1 or F2 is either use F1 or F2, both of them, it gives the same Wilson loop expectation value. So we get the square of the same quantity, and the square of this quantity is made of the W02 square plus 2 times W02, W10. So this one has no zeros, no poles, and that's the contribution exactly we have in this expression. So here's the zero instanton and single instantons, and here you can see zero instanton and single instanton with factor 2. Now, contributions to one zeros is basically coming from the single particle object, which is basically there's W bosons and instantons, and they are connecting this flavor to this flavor. So whole thing is playing a single object, so they have simple poles. But we observe that this pole into the chemical potential, 2 of them. So we have to have a zero, even though we killed off the one pole with the zeros. So that's the contribution, and this contribution bounding these two flavors cannot exist without instantons. So one could think about contribution with the zero instantons, which I ignored, but you can just add the W bosons here, then you have number 1 there, I think, which will be obviously has no poles and no instantons, and that could be regarded as a classical part of it. But so this contribution starts with instantons and non-trivial instantons, and that's exactly this quantity given here. So there are double poles, and remember in Kopakuma buffer invariant, every expansion is in terms of P1 over P2 or P1 times P2, but this pole structures is just made of P1 and P2, and this doesn't allow angular momentum interpretation of the SU2 left and SU2 right. So you have to take this as just the structure of the this configuration Wilson loop expectation value. So there's finally there is another way to calculate it, which is refined holomorphic anomaly equations. And this subject I'm new to. Some of you may know very well about this. So Min-shin and Shin-Wang is expert on this subject. So we venture into a different way of calculating these expectation values. Now, so remember, Kupakuma-Buffer invariant is Z is a plus the log of the free single particle free energy. But if we do the ordinary exponentials, then we have to sum over all this expansion with log 1 minus x has a power in 1 over n. So we have this n's power and sum of n with n goes from 1 to infinity. So that's the log of the free energy. So it has much more complicated structures. Now this free energy, we expand in terms of the power series of epsilon 1 plus epsilon 2 and epsilon 1 times epsilon 2. So when this contribution is 0, it is unrefined expansion, genus expansions. And TC is basically chemical potential for electric charge and magnetic charges. So that's the Keller structures of the geometry. Now, one knows n and g goes from 0 to infinite, and you can see that when g equals to 0, there's a photon in 1 over epsilon 1 and epsilon 2, which tells us something about the single particle nature of this object. And with a certain small value of this, one can know the small value of this. And when ng plus m plus g is bigger than 2, one can expand in terms of these chemical potentials or Keller forms, and that its coefficient is called Gromov-Witten invariant in B model. Now, this quantity expressed in terms of B models, which is mirror symmetry, so we are changing Keller parameter to complex structures. And then this prepotential will be depending on complex structures, but it's not completely holomorphic. And there's an anti-holomorphic part of it, and there's a defined holomorphic anomaly equation for these topological strings. So one can regard in a P model as an amplitude of the type 2B theory, where I guess a string is mapping to the mirror geometries, and this is the defined holomorphic anomaly equation. And with a certain initial conditions, and this is a sort of a recursive relation, because the right-hand side, the contribution comes from lower number of n and g's. So if we know that certain initial conditions, then one can solve this equation recursively, and then confirm one can obtain Kupakuma-Buffer invariant from this manner. One can obtain Gromov-Witten invariant from which one can build up the Kupakuma-Buffer invariant. Now one can do something similar with Wilson loops. So one can, as I said, that one can define the free energy with Wilson loops. Then one can define the these expansions with. So one has to be careful about zeros, terms with zeros, and then one can build up the holomorphic anomaly equation for Wilson loops, and then one can solve this recursively, and then one can confirm the result obtained using solving these equations. So interesting thing is because of zeros, again, from P model perspective, one has to be more watchful about the mathematical meaning of the map. All right, so that's the end of my talk on 5D Wilson loops. Is there any question?
Actually, may I ask a question, Kimyeong?
Yeah.
This anomaly equation, is it related to the topological recursion?
Right. Right. So, I mean, because some sense we're in easy place, some sense, because remember using the what is it, topological vertex method, we have already have a procedure to obtain the reasonable expectation value from the case with 2 additional flavors. And this chromophoeton invariant for this case is there's no problem. And then only thing is we have to take a very careful limit, such a way that we have a constant refined holomorphic anomaly equation for Wilson loops. So if one wants to build up from the scratch, it would have been more difficult, but because we know how to do that with the flavors, that's how we approach it.
Mhm.
All right, so this is related but somewhat different topic. It's 60 Wilson loops. And this is the work built on the series of work done by Babak and Hitchell and Marcus and so on. So in here, we just explore the new cases, but let me just start with some general statement about 60 Wilson loops. So in terms of here, we have considered in different contexts. So we have to consider both the codimension 2 and codimension 4 defects. So for example, one can start with 60 series with say multiple NS fibranes. If we have multiple NS fibranes, then one can regard the NS fibrane is in 2A series. We can regard it as M fibranes, then that's the Tucumajero series. But we can introduce D6 branes. So let's think about 2 D6 branes with multiple NS fibranes. And that's the theory SU2 with the tensor and the SU2 KD group, and then 2 flavors on each side. And so this is the quiver theory of that type of series. Now one can do Hicksing of this theory, which means that we are pulling out a single D6 brane out of this arrangement of multiple 2 D6 brane going through the NS fibranes. And during Hicksing process, we can always, from field theory perspective, we can generate the magnetic flux vortex, which is localized in 2-dimensional plane. And similarly, when we pull that out from brane perspective, one can generate D4 brane. So D4 brane on D6 brane is like a magnetic monopole, but because of Hicksing, it's localized, so one can regard it as a flux vortex. So here's a D4 brane. World volume is 0, 1, 2, 3, and then pulling out the 7th direction. So it's localized on origin because we do omega deformation. So it's codimension 2 because it's a transpose direction in 2-dimensional. So that's one can build up the codimension 4 defect, 2 defect in this remaining theory, which is made of single D6 branes and multiple NS5 brane, which is basically Tucumajero series. Or similarly, one can build up the codimension 4 defect by, say, start with SU3 series, and then we pull out D6 brane to this side and D6 brane to the other side. So we have 2 D6 branes, and then we have NS5 brane. D4 brane connecting M5 branes, NS5 branes. And then, so we have 2 vortex sheet from the 60 perspective. Then we are pulling this D4 brane with the double Hicksing, basically. So pulling out the D4 brane out of NS5 brane. And during this process, we can generate another vortex, magnetic flux vortex from D4 perspective, which is from the NS5 brane perspective is 0, 1, and the 6 directions. So transpose direction is 4. That's a codimension 4 defect, or this is the Wilson surface from the Tucumajero perspective. So there are many different ways of generating the Wilson surface, but one can do it by double Hicksing. So one is interested in similar object in what we have done is S of 2n gauge theory with 2n-8 flavors, and there's single tensor coupled to S of 2n gauge symmetries. Now we are interested in partition function of this area on R4 equals T2 is omega deformation. Now self-dual string with respect to this tensor branch is also instantaneous string of SO2n. And we are interested in expanding this partition function in terms of a perturbative part and stringy part. And stringy part will be expansion in terms of k goes from 1 to infinite because there are single kind of strings. So you can go from k goes from 1 to 0 to infinite. Now, one can calculate the partition function. Perturbative part is well known. And one can calculate this partition function using the 0,4 quiver theory to the on k strings. And because the kg group is SO2n, instantaneous string will have a USB2K kg symmetries. And then this calculation can be done easily using Jeffrey-Cohen residue method. And this, for example, result for single strings. And this has been obtained by Kumran and Babak and their friends some time ago. Now, the thing is introduce, say, codimension 2 defects, for example, which is localized on X4 and X5. And in this case, now, instantaneous dynamics will be changed because of presence of this codimension 2 defect. So one can obtain partition function using the modified instantaneous dynamics, or one can do very easily using Hicksing. So one start from the gauge group SO2n plus 2 to SO2n, and one get partition function for SO2n plus 2, and then which can be done in this manner. And then we just Higgs it with this additional fine tuning of the parameters. So during Higgs process, you are reducing the flavor symmetries. So you are this flavor chemical potential is fine tuned to this omega deformation parameters. And also one introduce and also one removes the additional gauge holonomy parameters, but such that we keep the this X parameter. Remember, there are 3 parameters, so 2 flavors are gone and 1 gauge parameter is gone. So there is 1 more parameter which we call X, and so with this fine tuning, we can go back to this partition function and then insert it. Then resulting partition function is one is codimension 2 defect contribution. So resulting partition function is made of again 60 perturbative part of SO2n, and then there's 40 perturbative part because for the theory this codimension 2 defect. If you go back, then here's codimension 2 defect. So this is localized on 4-5 directions, but still there are degrees of freedom living on the 2-3 directions. So just epsilon 1 contribution pole terms, and then there are things moving with speed of light along the 1 direction, which will contribute to the index. So this will be perturbative part, and then there are stringy part. And stringy part, again, is given in terms of modified JSM, but this Higgsing processor generates the answer right away. And so, as I said, this contributions has poles at epsilon 1 equal to 0, and there's no poles because it's localized at X4 and X5 already. Now, codimension 4 defect, as I said before, again, one can do JSM, but easier way of doing is double Higgsing. So, so one start from SO2n plus 4, then we reduce the 2 gauge charges and also 4 flavors. And along the way, we introduce a single this chemical potential. You can see that both of them we define as single chemical potentials. And with this fine-tuned partition function, now we have a SO2n perturbative part coming from the single string, this codimension 4 defect, and then there is a contribution from the compositions. Now this composition as a contribution, you can see that q to the minus 1/2, because this captures the nature of the this four-dimensional four defect being fermionic. So it has contribution minus 1/2, one can see easily. And again, Kuiper theory with JK residue generated these answers. Now, paternity part, which is just a 2D contribution, is a 2D fermion, and the 2D fermion is momentum moving with speed of light, is basically given in theta functions, and theta tilde is made of theta divided by eta functions, theta and eta functions. Now, this codimension 4 defect localized this R4 has no poles because it's localized already. And we can re-express this partition function in this manner. So we are expanding this composition of the this using codimension 4 defect with self-real strings, which number is given by k, and so on in this manner. And this structure is dictated by having an oriented fold for SO2n case. And so its contribution is N is basically ranked gauge groups. And the Wn, again, each this tests the structures of the representation of the, remember, Wilson loop can come with various representations. And when you insert this fermionic string to the SO2n theory, you are not specifying what representation it belongs to. It's not like a fundamental string coming in where we can define the child explicitly. And so Wn is a Wilson loop operator for different representation of SO2n. It's basically a trace to fight the 2n from the scalar field contributions. And it satisfies multiple provocations, also similar to Sungjae, Hichal, and Min-sung's work. One can use the Blow formula to calculate contributions. Here are contributions for single string and this perturbative part of it. Of course, we have obtained this also from the Higgsing, and they are consistent with each other.
So
and,
can I ask a question?
Yeah.
So you call it a Wilson loop, but is it actually a Wilson surface?
Yeah, it's Wilson surface, yes.
And do you know that Wilson surface is parameterized or labeled by representations of the gauge group?
No, so here, so you can see that when we introduced so Wilson loop is basically self-real string with respect to NS5 range, right? And then on NS5, between NS5 range, there are various gauge groups. So interaction is more delicate. And that's why this this partition function is summed over all the representations of say pi to 2n. So this one characterizes the representation. So it's a little different.
Different, but
so
something is labeled by representations of
and right, and characterized the representation. Yes.
Is it related to what, the Young diagram?
This SO2n, so you don't have a Young diagram. So I'm saying that this one tells more of the way the so we haven't explored fully, but we know that this is related to how brain is interacting with brain pictures, and so this one tells something about how this object is interacting with original brains. Yeah.
Well, then do you have a field theory construction of the Wilson surface operator?
We have one can do the fermionic strings, so one can do the GLSM on instantons, but remember in GLSM on instantons know the instant Wilson surface, And also it knows the gauge group, but gauge group and Wilson surface, interact not quite directly. So.
Okay. Okay, thank you.
Right. So what it does is the basically quantization of the classical Seiberg-Eaton curve. So for this TDR version of this SO2 and gauge series, and one can, from this TDR version of it, one can easily write down the classical Seiberg-Eaton curves, and also maybe you heard from many other talks that one can quantize this in NS limit, and that's what we would like to do. So we want to express this partition function of codimension 2 and codimension 4 defect in terms of the various exponentiated chemical potentials. And additionally, we introduce the y variable, which is exponential of minus epsilon 1 del over del x, which is a difference equation on these objects. And we have shown that, for example, when we act y object on this codimension 2 defect, this misleading 4D, 2D, so this codimension 2 defect, because we are looking for the object on 6D object. And in the limit where epsilon 2 goes to 0, which is NS limit, when we act on it, is same as the partition function of Wilson surface times this quantity. So Wilson surface naturally appears as eigenfunction of the these difference operators. So one define a wave function psi x as the ratio between NS limit of this codimension 2 defect divided by partition function without anything, and then chi x as a sort of ratio between this NS limit of the codimension 4 defect divided by original partition function. And with this definition, one can show that this normalized wave partition function satisfies following difference equations. And here's a difference operators, and then there's inverse, and there's various contributions, and then these contributions. Interesting thing is, remember these wave functions has perturbative power plus instant contributions or string contributions, and similar to chi-x. So one has to confirm this differentiation order by order, and that's what we have done up to 3 strings. And also this, again, codimension 4 defect partition function can be re-expressed. This is the NS limit of that codimension 4 defect partition function. And this H can be regarded as a sort of codimension 4 partition function in NS limit. And this equation, if one takes a careful limit where epsilon 1 goes to 0, then it becomes this above difference equation becomes the classical Seiberg-Eaton curve. So this is a quantization of the Seiberg-Eaton curve in NS limit. But this one has a lot more physics than what it appears, and we are just scratching the beginning part of the stories. So let me conclude with some remarks. So there are many approaches to Wilson loops, gauge linear sigma models, blobs, topological vertex, holomorphic anomaly equations, and Higgsings, and they are all constant to each other, and they have a good side and a difficult side. And Wilson loop appears also in quantum difference equation, which is quantization of Seiberg-Eaton curve. And I'm sure they will play an important role in quantum integral models. So higher rank, not only quantum difference equations are there are many integral models, and they'll play an important role there. And codimension 2 defect in 5D also play a role of wave function in quantum difference equation, which I haven't explored at all. In 5D theory also, there are magnetic monopole strings and their corresponding Tupte surface operators. And Wilson loop and Tupte loop operators would play a generalized Velindo algebra acting on some partition function. I think that Yoshida worked on it a little bit, and there are still a lot of work to be done. And so PPS defect in 5 and 6 dimensions have more structure to be explored. Thank you.
Thank you very much. So, very interesting talk. So it's time for questions. So if you have a question, please.
Excuse me, can I ask?
Yeah.
So in your talk, so you consider codimension 2 and 4 defects, but are there, say, codimension 3 defects in, say, 5 or 6 dimensions?
Oh, so to be constant is a supersymmetry, there's some constraint. So 5D, I just said about codimension 1 defect, which is a Wilson surface. Okay, I know Tufte operator, monopole operators and corresponding Tufte operators. Codimension 3, I'm not aware of it. Maybe there's such object with some interesting tinkerings.
I see.
And also, as I said, these objects are related also higher form symmetries, and that's also quite interesting direction. And we are looking into it.
Okay, thank you very much.
Any other questions? Kim, can I ask a question about your final comment about, you mentioned some generalized Berlin operator algebra.
Right.
Is it something related to a rational conformal field theory? This is Berlin's NU algebra, or do you have in mind something different?
Oh, right. Well, I guess Okuta-san is more expert on this, but I'm saying that even in 4D theory, there are also such a Berlin operator algebra for half index, where you have S3 cross S1, then you do T3 cross S1 partition function, which can be regarded as some sort of wave function. And then introducing what is called the Tufte operator, Wilson operator at the north pole of S3, it can be represented in terms of like operator acting on the half index. And then they satisfy very nice some algebraic structures. So I assume not only 2D theories, you can be generalized to 5D and 6D with a proper modification. And
I see. What kind of algebra does it have? Is it something related to something we know, or something quite new?
Yeah, I think it's related to what is known, and it is yeah, nothing is new. I mean, it's always refinement and modifications.
But it's something similar to what we find in, I mean, rational conformal field theory.
Right.
I see. But that appears in 4D.
Right.
Yeah, in 4D, this appeared. This is for non-rational conformal field theory, like Duville or Toda.
I see. Thank you very much. Any question? Okay, so it's not. Let us thank speaker again.
All right.
So we just